Really, we have an intermediate layer.
Okay.
I'll come back to you.
So, we have a group of folks from Bell Labs. Bell Labs, by the way, is a part of Alcatel-Lucent. So I'll be talking about Bell Labs mostly here. And and you heard some of the presentations, some of the work that we've been doing. But before I get into one deep topic that I will get into some more detail, I'm not going to talk about a generic vision, but I will get into one area, in fact, which matches very closely with what Dan Kaufman mentioned at the beginning. How do you bring network and cloud together? So first I'll just show you, Alcatel-Lucent. It's a company, it's headquartered here. Headquarters are right next to Eiffel Tower. They used to be in Lavoisier, they were moved recently. This is a fairly global company. It has, let me see, go back. Okay, so this company is in about 130 countries, and the revenue is kind of equally divided between North America, Europe, and the rest of the world. And there, it's in 130 countries and a fairly large company. And Bell Labs, this is what I'll be focusing on. It has about 1,000 researchers, and it's a worldwide organization. And in fact, I think all the steering committee members I met here, their students, are in one of the locations at least. And also, I'm sure this is true for folks here in Rio also. So, again, our main mission is to try to help Alcatel-Lucent in coming up with differentiating products. But in addition to this, we also try to define the future also. What are some of the breakpoints that are going to change the world? Sometimes the business units are not too happy about it. I'll give you one example of this. This was back in 98, 99. There were a bunch of researchers at Bell Labs. They went and told the division that was building these large switches, something called 5ESS, and there was probably, that was from Lucent, and there was a similar product on Alcatel also. So these guys, when they said, whatever you're doing is going to disappear, and they were laughed out of this place. So this was, they had a business of something like $10 billion, a profit of something like $6 billion, and this happened. So our job is to kind of identify discontinuities. Another example was there was a student of Henning and his student, Jonathan Rosenberg, they were working on SIP. So initially, again, they got a lot of resistance, but again, look at the world, how it changed. So it's not just, our mission is not just to help the business units, but also to identify some of the technologies that will change. For example, flat wireless networks is another one. So again, it's to help into the marketplace, but also look into the future also. So now this is a global organization. Mostly most of Bell Labs used to be in New Jersey, but now after let's see what happened.
You need a better connection.
Okay, a better connection.
Yeah.
Okay, all right. Thanks for pointing this out. Okay, let's see. Okay, so again, New Jersey is one of the major locations, but there are three major locations here in Europe. There's one south of Paris in Varso, there's another one in Antwerp, and then the third one in Stuttgart. So these locations have something like 200 to 300 researchers, and then there are smaller locations around the world, as you can see. So I'm not going to go through, but it's a global organization. So, and as I was talking to the members of the steering committee here, it seems the students are in many different locations. It's not just, in fact, one of his students is in India, yes, right? Okay, so again, Bell Labs, has an illustrious history, goes back from like 80, 90 years. I'm not going to go through. I just want to show you one picture, because sometimes people believe that this is the past history. There are three winners of national medals of technology from Bell Labs. So this is Herman Kogelnik. He's the godfather of optical networking, as you know, things like WDM. He created a team that's probably the best. And then this is Jim West. He did a lot of research on speech processing. This is El Cho. He's almost a contender for, and almost got Nobel Prize for his work on some material MBE process. So, and then there are a bunch of other awards that we have, Bell Labs has won in the recent years, but I'm not going to go through that. Probably many of you know this. Now, this is a bunch of inventions that Bell Labs has made over the years, so I'm not going to go through this. Many of you probably know this. I just point out cellular concept, and more recently something called light radio. This is something where these the antennas will be like in the form of a cube that you can put even behind billboards. So then there are a bunch of other inventions. I don't know how many of these you can see. Can you? Let's see. Okay. All right. Okay. So this is information theory is the most important one in that one. And let's see again what's happening. Okay. And let's see. So again, perhaps most of you know there are a bunch of good inventions that have been made in recent years. For example, one of them is photonic integrated circuits. This is like you have photonics and silicon transistors on the same substrate. In fact, the last talk was on how do you interconnect things together. Something like this probably will be fairly exceptional in terms of this, So I'm not, as I mentioned, I'm not going to give you a vision of, what. Let's see, what's going on here?
I think it's
Disconnection. Is this connection? Okay, so I'm going to talk about one program we have, which is, I would say, is the flagship program of our networking research today, something we call network cloud. Okay, so clouds are important, all of you know. What clouds have done is basically they made computing like utilities. Similar things happened in the Industrial Revolution. What happened was factories could produce equal to whatever their source of power used to be. But once there were electrical utilities, then they could produce as much as they could, and this really changed the world. The same way computing is also changing. This is an example, curve for startup that was started in New York, something called Animoto. It was a small, it was a very small startup. It had something like 5 to 10, servers. This was hosted in Amazon Cloud. Then there was an article about them in New York Times. And suddenly the number of servers they needed went up to, you can see, something like 5,000. But an interesting thing is you also see that it's going down also after that. So they had really no difficulty because it was in the cloud. So again, this appears to be a fairly mature area. So what can we do in this area? So here is a new angle. Again, this is something that I would like you to remember. Now, if you look at current cloud computing centers, these are huge data centers, as large as 11 football fields large. They are very close to the sources of power. And here, you can host applications that are done more in background, but they result in high latency. So the version of cloud computing that we are proposing, and in fact, we have a product that's based on this also. By the way, this is an example of something where there's very good research being done. Also, there is a product also coming out from the company. Okay, so what we do here is that we spread out computing resources in many data centers. And these data centers are put in central offices of these companies. Now, these data centers are right next to the access lines. So what this means is that you can really deal with very high bandwidth applications. Also, the delays are very, very short also. So that's why we call this network cloud. Now, the first chart that Dan presented, he had 3 themes. This was one of them. So in fact, we have a major program in this area. So again, it's fairly obvious that approach like this will help in dealing with low latency and high bandwidth applications. And again, this also has fairly high fault tolerance because there are multiple data centers together. So essentially these data centers along with the network will be like a large virtual data center. Now there are very interesting research problems that come here, which is that how do you do resource allocation or something like this. Traditionally there has been work done on resource allocation in networks than in data centers. But this somehow brings both of these two together. So one of our top researchers, well, many of you know him, T.V. Lakshman, he's leading a group in this area on the research. But there are a number of other problems that we are working on also. Let me just get some more. So this is a picture of the same, which is that there are these large data centers at the top, and then at the bottom we are somehow bringing everything together. And there are a bunch of these small data centers.
Krishan, are you saying this is a replacement for large data centers, or this is in addition to the large data centers? You may want to have some at the edges.
Oh, this is not a replacement for data centers, because this solution is not going to give you cycles at the lowest price points. For that, you go to these huge data centers, but there are applications that require. For example, I'll show you one application where what we want to do is, in fact, we take SDN concept to an extreme. This is something I'll show you. We have a product called light radio. In fact, it's a product concept. Parts of this being done. So what you do is you put these small radio heads everywhere. Then you have a fiber that takes these radio signals, get sampled at twice the maximum frequency. You send these samples to a data center, and this is where it's processed. Now, if you're going to send them somewhere close to Hoover Dam, that's not going to work. So an approach like this is really very important. So this is like, I would say, niche market. But could be, I believe that this would be, a very high margin market. And this fits in very nicely with what service providers do. So in fact, we have a product from Alcatel-Lucent that's called a cloud band. So research teams are working very closely with them. This cloud band, this team is headquartered in Israel, and there's really a very close relationship between the research teams here, between Bell Labs and this one. So in fact, I'll talk about some of that research also. So again, this is just a vision of how this cloud computing has evolved. First, there were these data centers where you could go and rent a cage, and you will go and put your own servers in them. Then what people found was that these servers were not being used very well. So then there was a company like VMware. They come up with virtualization solutions. That means for a single customer, you can share. Then again, there was you can do further statistical multiplexing. This is the conventional cloud computing. These are elastic clouds like Amazon. And what I'm talking about here is a network cloud. We are bringing network and clouds together. So this is like a niche for Now this opens up a lot of interesting research problems. In fact, it's amazing the amount of interest that has generated within the labs. So the first one is, when you have all these small data centers and network connecting them, you need to even find out what is out there. So you need to do a discovery of resources, both computing, storage, as well as for the network. So you gather this information, but this information has to be somehow abstracted out in some form so that you can apply some reasonable algorithms to them, and then you have to send them over to a resource allocation scheme. So for this, we are using a payload protocol that ITF has defined, something called ALTO. ALTO is just a payload protocol. There are a lot of algorithms that go behind it also for abstracting of network, etc. Yes?
So does the customer have the capability to shape the quality of service, or it's only the provider who does it?
Well, no, customer has, in fact, as I'll show you that. I'll show you a bunch of resource allocation schemes that we have worked on, and there are a lot of different types of constraints that you can put. Clearly, there had to be resources available in the network, and there's been a lot of interesting algorithmic work that has been done in this area also. So that I'll talk about. So first part I'm just talking about is the discovery of the resources, And for this we use this. Alto is a protocol that was defined by the peer-to-peer community, but we are using that in this network cloud. So in fact, we have built a server based on this, and in fact, many of our business units are now using this also. Again, I want to emphasize, ITF just gives a payload protocol. It does not give the algorithms. There's a lot of work that's required when you get all this information from all these. For example, there are these peering systems in networks that do peering at OSPF level. You get that information. You get information from data centers, and you kind of merge them together. And then you may want to look at this information at different levels of detail. So there's a fair amount of work that's been done in this area. So, by the way, I've never understood how ITF comes up with names. Maybe there are some folks here who play a major role in ITF. Maybe they can explain to me. The name for ALTO stands for Application Layer Traffic Optimization. As I mentioned, this was done for peer-to-peer systems. And again, Bell Labs has played a major role in this, both in ITF as well as in IRTF. Now, I'll come to, I would say, subject that will be a lot of interest to this audience. Now, unfortunately, I do not have any equations here. But this work has been done mostly that I'm talking about here by T.V. Lakshman and his team. And he has a bunch of papers. So if you're interested, I can send you those papers. So again, as I explained before, we want to do resource allocation for computing, network, as well as for storage. And we want to have several level guarantees. So SLAs will not only have bandwidth, but also will have needs for the computing and also the delay requirements also. This is an online system, so that means requests come one at a time. You don't know what the future will be. So what you want to do is you want to allocate resources in such a way so that maximum amount of resources are available for the future. So this will help us in dealing with as many requests as possible. And again, we have done a lot of work on for different types of applications, for example, gaming, etc. Again, this is again a point which I made earlier, so I'm not going to go through. Problems like this have been solved for classical data centers, but for these resource placement in these network cloud is much more complex, because you can have all kinds of constraints. You may say that, oh, the delays have to be, say, less than 50 milliseconds. For example, by the way, I talk about cloud band, the delays there have to be like in milliseconds. And then there may be some cost limits also. Maybe there are some background type of computation that you may want to do in large data centers. You may not want to do in these small data centers. And then, delays is something that is the main value of this system, and that's something that we can specify. So user can come and say that I need to run this application. I need so much computing resources. I need to have say delay less than a certain number. I need to perhaps have information stored in two different places, so that if one of them fails, is information available somewhere else. By the way, there is a lot of money for something. The companies on Wall Street, they build private networks so that they can get information little quicker than the competition. So this is something which is very important for certain app. So let's see. Okay, so there are. This is a tough problem. You want to. Okay, what's going on here?
I think it's when you touch the cable.
Okay. Okay, so.
I think it's a cable.
No, I'm not touching the
When you
cable.
walk in.
The laptop?
The laptop. I think it's okay. I mean, you're losing it for just a couple of seconds each time.
I just want to see whether. Okay. Hopefully this will do better. So again, we want to admit as many users as we can. and the customers want to get the best service that they can. And then, normally in these cloud systems, you will, large clouds, you will say, I need so many VMs, but you have many more constraints here that you have. So this leads to a lot of interesting optimization problems that could be solved. In fact, this is what has been done. By the way, some of this work is already in this product that I talked about. So this is, how do you place these algorithms? How do you specify these policies? And how do you, come up with a scheme that gives you a fairly optimal result, but at the same time, that doesn't take forever to do it also. And by the way, as you will expect, that the complexity will grow with the number of constraints. So some of you know mathematics infinitely better than me. So this uses primal dual optimization method. In fact, I have a reference to the paper that T.V. Lakshman and Murli Kodlayam have used in this area. So this again, this is fairly obvious for this audience, which is that when there's a polynomial term algorithm, that's the optimal result. But if that's not the case, then you come up with an approximation technique, which is which is reasonable. It's like within a certain factor of the optimal results. So again, as I told you, that this is an example of something that is, has both great research as well as has had great business impact also.
Can I ask one question over here? So does the cost of the price automatically be determined at this point? Because if I ask a very stringent constraint, do you determine right there with the algorithm or separate?
The cost is a part of this also. You can say that I want it to cost this much.
I see.
So there may be non-feasible solutions also. You may want to pay 5 cents and you want a delay of 1 millisecond. So clearly, there's no feasible solution to something like this. I mean, this will compute on a solution only if it's feasible, right? So I'm not going to go through this with a bunch of these, as you will expect, different types of constraints. Yes?
I just had another question. I was wondering, one of the concerns I would have is that if you have database-backed web applications, for instance, stateful applications, but the cost of consistency goes up, because you now have to more likely synchronize across different
Yes, of course.
mini data centers, right? Which is typically something you're trying to avoid, like the plague today.
I see. Yeah, but I absolutely agree with you. So this is where you have to pick the applications that will make sense for something like that. For example, if you have camera networks, for example, London has something like, 100,000 or million cameras.
Right.
You don't want everything to go to a single data center, right? So you want to filter that, something like that, where they're kind of independent of each other. And what we call virtual telco applications. We want to put very simple network elements all over, and we want to bring intelligence in a common place. And again, many of these virtual telco applications have very strict delay requirements, and that you cannot do in a central place. In fact, there was AT&T, after they deployed, when they deployed these iPhones, so the signaling traffic on their network went up. So we looked into whether we could move this into the Amazon cloud, and we could not, because we would not meet the delay needs for AT&T network.
So is this primarily for your own, the network operator applications? All the examples you're giving are more like the telco application. Are there good end user applications for which you want to do partitioning like this? And what are the examples of end user applications where you can do partitioning like this?
Well, there's a demo that we showed at Mobile World Congress for this, and this is for virtual desktop. There is this problem of WAN acceleration. So if you can somehow bring the logic and the information close to the users, clearly that would be. So that's one example of this. I mentioned camera networks. Where you can filter information. Virtual telco is a third application. So there are a bunch of applications that I can think of. Huh?
Gaming, network gaming.
Network gaming will be another one, of course. Of course.
Yeah, but I think the Amazon type situation is where they're just trying to sell excess capacity, right, at low utilization time. So I don't know whether that's sometimes the philosophy of the cloud.
Well, okay. Cloud computing is like is to computing what internet was to communications. So essentially, you can do statistical multiplexing. So if you have big data application, you have like large data sets, MapReduce, etc. For that, something like these large data centers, you cannot beat them. This is not the solution.
Right.
Don't even try that. Doesn't. So this is like it's a complement to this other one. Again, as I mentioned, there may be even more applications for a system like this than for these large data centers. So there are applications where I make a case for.
So would you consider CDN to be a good application for this, for content caching and rather than
Of
caching
course,
it inside?
say CDN. Yeah, I mean, in fact, yes, you can put CDN also in this, and also things like even WAN acceleration, which
No,
is the logic.
what I'm trying to understand is maybe you can versus, do you think the CDN is the hottest application in some sense? So are you using this kind of stuff for CDN, or that is not the driving application?
No, that's not the driving application right now. In fact, we do have a CDN product called Velocix, which is, but so we're not really looked into. But clearly, of course, if you have data centers, small data centers right close to you in the central offices, of course, you can put content there also. And so,
Yeah, but the main issue is the latency. In fact, in Amazon, you have 3 very large data centers, and in the US alone, you cannot. You can reach only 70% of the population under 150 milliseconds. So if you need better latency, you have to go through something like that.
oh yes,
Yeah, so
right,
it's
right,
really
right,
latency,
right.
so-
Yeah, but again, I can understand for
Yeah.
some applications the latency is very critical, like the gaming is potentially one. This radio application you're talking about, I can imagine latency is very critical. But as soon as you have human in the loop application besides say gaming, why is that latency of another 100 millisecond matter?
Well, again, sometimes it depends on where the application is. For example, the typical example that gets used for WAN acceleration is if, for example, you put a file in a data center, and the program is on your computer. There are 50 round trip delays. So if the file is somewhere, say near Hoover Dam, it will take something like 5 seconds before you can, get a response to anything you do. So that's probably not going to work out very well. So again, there are applications that are going to need this, but that applications that don't require that, and clearly you can do much better. Also, another thing about this is that since this is very close to the access lines, the bandwidth costs are much lower for backhauling all the way back to. So that's another one. So again, this work, I have to say that even this business is in early stages. This is something that, clearly companies that have these large data centers, they're well established. Service providers are just getting into this space. But then they need some differentiator so that they can get in the business.
I understand that the service provider differentiator is you have all the COs and you can deploy
Yes.
something interesting there, but then you have to also say what applications are amenable to partitioning,
Right.
computing in this particular fashion to give you that edge that you're looking for.
Well,
Like the radio application you're talking about, that is for the benefit of service providers themselves. It's not for the benefit
well,
of...
it will reduce OpEx and CapEx for them, right? So,
Right.
but then there is gaming, there is camera networks. So these, and I would virtual desktop, which is that if you do it in a large data center, that probably the performance is not going to be very high. So in fact,
Yeah, okay.
So in fact, I believe that demo will be shown at SITCOM this year also. So if you're there, you could probably can.
But for some of these applications you're talking about, if this resource allocation problem that you're describing, is that really that dynamic? Because, for example, virtual desktop, you pretty much know you need a VM and so on. So the very generic resource allocation problem description you're talking about.
Okay, so there are two parts to this. There is something that's going into the product. There's other one which our researchers find to be very interesting. And some of this work may never be used also,
Sure.
but some of it's being used. That's the important part, right?
I think one application we're going to see for those
Yeah.
distributed, more distributed clouds is when the Internet of Things will really grow massively, and we will, as I mentioned yesterday, I don't see all the data that will be collected by the sensors, all
Right,
the description of the different things in the environment to be somehow centralized in the big data centers we have today. I think we will need some intermediate devices that will do pre-processing, that will definitely store part of the data, filter part of the data, and that will run several applications at the same time, because we are going to use those things for different type of things. So it's like the application
No, I agree with you.
architecture will be distributed
No, I
among
agree
the
with
data
you.
centers and those gateways. For
I
those
agree with you.
data things.
You know which was the fastest growing networking company for many years? Riverbed. Why did they, why did they were so successful? Because of all the problems with their Microsoft applications. If they move them into data centers, it caused all sorts of performance problems. In fact, just Alcatel-Lucent has a few hundred of these boxes just to speed up workload. So again, all this thing when we say that we're going to centralize everything in a data center, sounds very good, but it has issues. So in fact, if you look at what Riverbed does is they put appliance close to you and close to the servers. So they're solving some of the problems also. So again, an approach like this could also be used for the WAN acceleration also, not in individual boxes, but in by the network operators. So I'm sure that if we come up with infrastructure like this, there will be many applications that people will think about. So again, now I just want to briefly mention a program we have that's the part of this network cloud program, this being in operating systems. There's a person not too far from here in Antwerp, Sapi Melander, many of you probably know him. He's building this operating system. And this again, the focus is on reliability, real-time operations, which something will support these virtual telco applications, and also for high performance, it's also very important that the time for switching between applications is very quick also. So again, so he has come up with a bunch of techniques for doing this. In fact, he's building this system. So I don't know whether you know Sapi, right?
Yes, of course.
Yeah. So I don't know how many of others know. So he was a professor at University of Twente, and now he came to Bell Labs in Murray Hill. Then, after we started a location in Antwerp, he moved back to this area. So again, this is an interesting area. This is something that perhaps we can have further discussion about. So this is like a fairly large effort, all the way from business all the way up to this, So the person who runs this business, his name is Dole Schooler. He will not stop praising the researchers who helped him. So every time I see him, so this is like a good example of something that which has both meaty research as well as business impact. Again, it remains to be seen whether this approach really takes off. I have to clarify that.
There's another issue related with this, which is the federation of those clouds, because it could be a unique cloud that will be distributed, spreading out of the data centers,
Yeah.
or it could be the federation of the largest one with smaller local regional
Oh yeah, of
clouds.
course you can say that the persistent information is kept in these large data centers, and to bring these processes close to the users. That could be a
Right.
model that could be.
And I was talking about this with your colleagues in Israel a couple of weeks ago.
Oh, I see.
And I understand that Alcatel-Lucent has today an interesting solution for federating clouds.
Well, yeah, I'm sure they're doing a lot of interesting things. In fact, I was talking to Jim about this. One of his students is going to join this group soon.
Who's already there?
Already there? Okay, good. Okay, I'll ask you for his name. Okay, good. Okay, so next I'm going to talk about new virtualized cellular infrastructure. How much time do I have so that
You can finish in 5 minutes, I believe. It's okay with you? Or you
Okay,
need
can I
more
have
time?
what, 10 minutes?
This one is not open.
Okay.
Yeah, sure.
10 minutes. Okay, I know that, Okay, so again, these, I'm sure all of you have seen these curves. Because of these smartphones, data traffic is on internet is growing even faster. So in 5 years, they expect something like 5 times, 30 times the growth in traffic. So they expect something like 2.5 billion smartphones. Out of there are, by the way, about 6 billion phones today.
And the service has been going to zero also.
Yeah.
So
Well, the reason is the amount of bandwidth that is available is, so again, I don't know why this is, let's see, why there is a problem here. Let me just-
It was when you change it in order to
Maybe just try it.
Keep it like this.
You can see it, it's okay.
Yeah.
Yeah.
Okay.
Oh, okay.
Okay, fine. All right. So this is better. So if you look at like a major US city, you need like over 2,500 base stations. And there's really, as you would expect, that the infrastructure would be extremely large for something like this. So what are some of the solutions that we have? One is you can come up with better air interfaces. You know, there's LTE, LTE advanced. I don't know what is beyond that. I've been asking people. I don't think what could be the 5G. And some of you have answers probably. The other one is, you know, you do reuse small cells and femto cells. And this is a very powerful solution. But again, this is a very tough problem also. The reason is that service providers, they don't want to allocate separate spectrum to small cells and to macro cells. Because, you know, paid billions of euros for these licenses, and they don't want to, you know, have separate channels for each one of them. But if they start sharing the same channel, then there are all sorts of interference problems. So by the way, this is a area of research. In fact, yesterday, Francis Basili, some of the work that he mentioned is, and again, there's a fair amount of work going on in other parts of Bell Labs also. Another one is that, you know, you try to use spectrum in a more clever way. So in fact, there's a lot of work going on using TV channels. You know, they're not being used much. So there is this capacity. This is kind of reaching a limit. So the best approach to deal with this is to kind of find a way of you know, doing sharing, as is done in packet networks on this infrastructure also. Again, this means virtualization, means statistical multiplexing, both for the physical infrastructure as well as for spectrum. So again, if you look at, you know, there are two parts, as you know, actually three parts, but I'll just focus on two, which are the ones that really matter here. The control and data. The one I'm not going to talk about is the management plane. For the control path, you know, the requirements on processing are very, very low. So you can easily do it on any cloud infrastructure, but the delays are a problem. And by the way, this is where network cloud solution will help a lot. Now, if you do data path virtualization, that's much harder because, you know, now you have to process payload, and this is where you need data centers that have specialized hardware, including GPUs, DSPs, etc. Again, there's a spectrum sharing, but I'm not going to talk about it here. So there is a product that was announced by Alcatel-Lucent that's called Light Radio. So the idea here is the following. You know, you have a very simple radio head which has transmitter and receiver in it, and there's some circuits in that will convert the radio signal into a bit stream. This will be compressed. That will be sent over a fiber to pool of processing units. And the pool of processing units will be doing baseband processing also. This almost sounds like science fiction. What you're doing here is you take the radio signal, you are sampling it at twice the, you know, some of the electrical engineers, you know, it's twice the maximum frequency, and then you're sending the signals to a common place. And the signal processing is done there. So, by the way, operators in North America and Europe are not really much interested in this, but in Far East, companies like China Mobile, they in fact are strong believers in this approach. Because normally, you know, here as you can see that, you know, you need a lot of bandwidth to carry information to this, you know. So, but if you have dedicated fibers, that's fairly easy to do. So we have these cubes. Then there's a system on a chip which will be used for virtualization, and again, this infrastructure will be virtualized, and you'll be able to run multiple standards. That means like a converged radio access network. So this virtual telco applications that we talked about, you know, these they cannot be done using the current cloud solutions, and again, we need to have this solution like what I just talked about, network cloud.
What you mentioned before, it's using a CPRI or another
CIPRI.
Simple.
There's a lot of work being done on making it more efficient also.
Mhm.
So again, the first application is really some infrastructure small cells. This, what you vision that I outlined, this is more in futuristic. This is something industry seems to be moving in this direction. So again, this is perhaps is an example of a software-defined network taken to an extreme. Right? You're doing even radio processing in the cloud, right? Okay. So there was one restriction I mentioned. Now you cannot do data plane processing in general-purpose processors. So we have a research program at Bell Labs, so we're trying to see whether this can be done. For operating systems gurus, this is like just to show you the requirements. You need 200 plus giga instructions per second. You need the real-time needs is like 3 milliseconds, and there's a jitter constraints at 25 microseconds. By the way, there's a paper on some of this research that will appear at Mobicom this year. So this is a very interesting project we have here. Something I don't think will be something that you will see in a product in a few years, because a lot of these base stations today use ASICs, etc., to reduce costs. So this is really pushing the envelope. Not only you're going to do now sampling, but you're now going to do processing on general purpose processors. And to be able to meet these types of real-time needs, I mean, some of you have built these systems probably know it's not going to be easy. Probably going to be extremely hard, maybe almost coming to limit. By the way, a lot of this work, on this light radio, the cubes are being being built in Stuttgart, not too far from me. So they're building all sorts of cubes, high power, multi-band, all sorts of things. And there's really a lot of work being done in this area. So, very briefly talk about software-defined networks. This is something that Guru and I go back many years. In fact, Guru used to, many of you, I don't know how many of you know, he started the Genie program at NSF, which is like a granddaddy of all the next generation internet programs. So I remember I went with a group of researchers to talk to him about something called soft router in those days. It has a fair amount of similarity to the SDN concepts. Clearly, I mean, Guru and Nick have taken it to a point where I don't think we are anywhere close, but there is some similarity between them. So we did. This is a precursor to that research. Now, our company's view is that this is a great solution for data centers and constrained networks like enterprises. But for service provider networks, where you want to have feature parity with the current MPLS networks, these probably there are 10,000 different features that have been done over time. That probably does not make sense. So for this, so folks have come up with an approach that's called software-driven networks. So essentially the idea is that the programmability that you have in the software-defined network, you try to do it in an existing network. But you need to be able to observe what's going on in the network, and need to be controls. So our current belief is that you can do observation fairly easily using Alto-like approach, but the controlling will be very hard. So this is some of the work that some of the folks are doing in this area. So again, this is a brief introduction to this soft router program. This was done a long time ago, and there was the whole network consists of a bunch of very simple forwarding elements, and the route computations are done in a few servers. And it's not centralized. I mean, it is like multiple these control servers, and each forwarding element may have control from more than one control element server. So even if one of them fails, another one fails. In fact, there was a question that came to Guru the other day: is this centralized? I don't think it has to be centralized. In fact, we had in our research we had come up with some ways of how we can do, hot standbys, etc. And something like this. So there were a lot of interesting research problems that we solved, and we found there were a lot of benefits of this approach. For example, if you're going to do OSPF computation for multiple forwarding elements in a single server, and you can see that convergence will be very quick. But there were a number of interesting problems that we came up also. For example, if you add a new forwarding element, how do you bring it down? Because there's no path to any control anymore server, so how do you bring it down? So again, I'm very glad to see that Guru and Nick are making such great progress in this area. So again, this is the work. I think this will be probably, in my opinion, will be the future. Again, I had to clarify. This is my personal opinion. I'm not saying it's the company's view, but for in the short term, or maybe in the long term, because things don't never go away. Software-driven networks. This is the approach where you try to provide the same functionality on the existing networks. If you look at the current networks, they have all these different things: protection switching, MC lag, FRR. They're like all these different features. So I think for any new approach, usually the question is whether does it make sense to build all of these features again on this network. So probably it does not make sense for that. But clearly, I think for that, I think the software-driven approach will be the right approach. By the way, both of them initials are STM. Okay, so we have a number of good programs with Linksys. So I have encouraged research from the team here. One suggestion I made to Dan earlier today was that Bell Labs is like this global organization, so if you can bring in people from some of these other places here, also interactions with them, that'll be very good also. So again, there was a presentation that was made by Giovanna yesterday. So again, I have a couple of charts on that, but she did a good job at that, so I'm not going to go through with that, with the joint work that's being done here. And similarly, Francis Basili also talked about the work on self-managed networks also. Self-managed networks, by the way, is a very interesting area. This is an area where a lot of interesting research has been done. There's some areas that attract a lot of great researchers, but somehow the practical impact of that has not really been felt that much. So self-managed networks is one of those areas. So there's been work done in many different parts of Bell Labs, and a lot of interesting work on distributed linear programming algorithms, all sorts of things, AI techniques. People have used all sorts of things to make, but its impact has been on small cells. But this is an area which is really very important, because in these service provider networks, operational expenses are majority of the expense. They are like something like 70% of the overall expense. So if you can somehow bring that down. So when we talk to service providers, they normally tell us they want the systems to be zero touch. So something like this is really very important. So I think there's the bridging the gap between theory and practice, I would say, is the main challenge here. So again, a lot of great work is being done here, and again, I'll see that that we keep working closely together.
Okay.